Okay, so we're going to have a look at what happens when we apply an alternating current onto an RC circuit. It's like a resistor capacitor circuit, and what I've sketched up here is the voltage of the resistor. We can see that as the alternating current goes through it, that resistor voltage goes maximum 0, and then in the opposite direction, maximum 0, and it repeats. So that's what we know that alternating current looks like across a resistor. And in fact, the resistor one's really useful because whatever the resistor voltage is doing, the current in the circuit is going to be doing the same thing. You can see I've shaded in the positive and the negative parts to just help us visualize when it's positive and when it's negative. We're going to think about how the capacitor responds to that flow of charge. When it's above the x-axis, that means the current's flowing one way, and below the x-axis, it's flowing another way. And so at that instant, when the current flow swaps direction, that's when our capacitor voltage is going to be a maximum. And in fact, it's at the point where the current flow is a maximum that the capacitor voltage is 0. So just by joining the x's on that graph, we'll be able to see what the capacitor voltage looks like in relation to the resistor voltage. And what we're noticing is that the capacitor is doing exactly the same thing as the resistor, but it's lagging 90 degrees behind whatever the resistor is doing. So down here we've got a phasor diagram for exactly the same thing. The resistor phasor is drawn on at 0 and about to increase, representing that t equals 0 point on the graph. If we draw on a capacitor voltage phasor at the same instant, it's going to be a negative maximum, but about to twist around towards 0. What's really interesting to consider is that at any instant, if we add the resistor voltage and the capacitor voltage together, we have to get the supply voltage. So we can create a triangle, and that's what the supply voltage is doing. So interestingly, in an RC circuit, the supply voltage actually trails a little bit behind what the resistor voltage and what the circuit current is doing, remembering that the resistor voltage is in phase with the circuit current. It lags behind by some phase angle phi. And this is useful for us because this is going to allow us to define a new property of these AC circuits, AC RC circuits. We've got the capacitor voltage, and we know that the capacitor voltage is IXC and the resistor voltage. And so what we can see from that, because the current in our series circuit must be constant at all points in that series circuit, in fact the length of these phasors must be just directly, the capacitor voltage phasor must be directly proportional to the reactance of the capacitor, and the resistance voltage phasor must be directly proportional to the resistance. And so we can define a new property which is a combination of the resistive and reactive components of the circuit, and we're going to call that impedance. We're going to say that the supply voltage Vs equals IZ, where Z is the impedance that depends on the reactive and resistive components of the circuit. And from looking at the relationship between those phasors and remembering that the resistance one is directly proportional to R and the reactance of capacitor one is directly proportional to XC, we can write down a relationship that links those to impedance. So useful things to remember are that at any point in the circuit, because it's a series circuit, the current must be constant, and the current is always going to be in phase with what the resistor voltage is doing. There is also a voltage across the capacitor, which is also proportional to the current, but that's not dissipating heat, that's just that capacitor is just acting to store energy in the circuit. The impedance is the combination of the resistance and the reactance of the capacitor. We can use that to find how the total supply voltage responds to the resistive and reactive components of the circuit.